Our speaker today is Egor Erovenko, and he will speak to us on behavioral epidemiology. Thank you, Egor. The floor is yours.
Okay, so thank you, Sandra, for inviting me to give this talk, and welcome everyone who's attending this talk live and then possibly watches the recording of this. So I wanted to, so the purpose of my talk kind of is a twofold. First of all, I wanted to show you some cutting edge applied math field, which is called behavioral epidemiology. It came to existence maybe only like 10, 15 years ago, 20 years ago maximum, really. So it's a very, very new field, and we have a lot of work to do. And I'm going to illustrate this field by showing one of the projects that we did a couple of years ago on COVID-19. And so this is a project that's done in collaboration with Fola Augusta from the University of Kansas. Fola is a true heart and soul of this project. I'm just a hack who did all the game theory stuff, but Fola is the driving force behind this. She gathered the team of researchers who did a lot of other things with this, and she calls herself a mathematician who pretends to be an ecologist. So she used to work in the math departments. Now she works in the ecology department, and she says that, well, she gets paid a lot more than what she used to get paid when she worked in the math department. And by the way, so this project, so we did this in 2020. It got published recently in BMC Public Health. And this project actually led to our joint NSF proposal that just got funded. So we got a 1 million NSF grant to continue working in this direction, to incorporate human behavior in the epidemiological model. So NSF had a special program, they had a special call in specifically this area. And our proposal, luckily, we only 8 proposals got funded, and we are in a very nice company of teams from UCLA, Duke, Cornell, and the like. So I gave this talk several times already, and every time I give this talk, I have to change these numbers. Even the abstract that I submitted maybe a month ago contained much lower numbers. So COVID-19 is still pretty much a thing. These numbers keep rising every single month. And of course, we all know that this COVID-19 is caused by this novel coronavirus. And the worst thing about many viruses is that there is no therapeutic treatment. There is no pill you can take to just make it go away. And this research also, because it was performed in 2020, at that time there was no vaccine available. So whatever I'm going to say will not include the vaccine. Right now, of course, we are working on the new models which include vaccination, but in this model, we are going to assume there is no vaccine. And because there is no vaccine, the only way to try to spread this infectious disease, of course, is to limit the contact between individuals, so to limit the spread. And this is, of course, based on this social isolation. But the problem with social isolation measures is that some people follow these social isolation measures to the letter, while some others just pretend to do so and they openly mock them. So in essence, all these measures, they depend on the voluntary compliance by the population. Well, we even observed some outright stupid behavior early in the pandemic, such as throwing coronavirus parties to get infected on purpose. And as always, there are some people who believe it's a government hoax and there is no COVID whatsoever. So I hope I convinced you that the human behavior is a huge factor in how COVID-19 is transmitted. And this brings me to this relatively new field of behavioral epidemiology. So we have this old field of epidemiology, which uses mathematical models to describe how the infectious diseases are spread and transmitted. But any model of COVID-19 that does not include the human factor is always flawed. And so we need to account for that human factor. And in mathematics, we usually account for human behavior using game-theoretical models. And here's what happens in this case. The strategies that you may employ in this game model are informed by the current state of the pandemic. Yet the choices humans make affects the epidemiological model. So you have this feedback loop, And we have this coupled model, which often results in fairly complex interplay between these two models because they affect each other. So let me explain how these models are set up. I always say that whatever I do is as simple as 1, 2, 3, and so anyone can do it. So there are only 3 simple ingredients that go into constructing these models. First, we are going to construct a purely epidemiological model. It's going to be a compartmental model of COVID-19 transmission. Then we're going to build a dynamic game model of rational human behavior, and then we're going to analyze what happens when we couple these models. Now, I would like to point your attention, this is a so-called dynamic game. So here's what it means. A dynamic game is something that where the strategies that individuals choose, they change with time. And this is appropriate for the pandemic situation when the disease has not yet stabilized, it has not yet reached the endemic equilibrium level. Whereas for some other established diseases, we often use a simpler approach. We use so-called static games. So we assume everything has reached an equilibrium, and then within that endemic equilibrium, we look for the Nash equilibria strategies in a static game. The dynamic game is a bit different because it constantly changes with time. So let's start with the compartmental model of COVID-19 transmission. And because I don't assume that anyone knows how to construct these models, I'm going to start from the very, very bottom, very simple model, and we'll slowly build it up to the model of COVID-19. So a simple example of a generic compartmental model of infectious disease is a so-called SIR model. So all individuals are split into 3 homogeneous disjoint compartments. S is susceptible individuals, I is infected individuals, and R is removed individuals, which can be thought of as individuals who recovered from the disease and they acquired immunity, or maybe they died and so they no longer can get infected. And of course, there is a transition. So there's rates of transitions, lambda from S to I, and then gamma from I to R. So lambda is usually called the force of infection, and in all models, it's assumed that it is proportional to the number of infected individuals. So it's some multiple of the number of infected individuals. And gamma you can think of as a recovery rate, or maybe the death rate. We can then describe this diagram using a system of 3 ordinary differential equations, which simply explain how population is moving from one compartment to another. So we know the rates of flow between the different compartments. Of course, the minus sign means that individuals are flowing out of that compartment, and then the plus sign means individual move into the compartment. And of course, if you have this model run for as long as we like, eventually everyone will end up in the R compartment because there is no other way around this. But this is not a realistic model of actual infectious disease. This is just a basic generic model. So let's start building some realistic approaches to this. Most infectious diseases have an exposed stage when you're exposed to the disease, but you're not yet infectious. So it takes some time for the infection to brew inside of you, and then eventually you'll get infection. So we add this exposed compartment. Also, notice that we have this closed system in a sense that we ignore the natural demographic processes, such as natural birth rates or natural death rates. And this is justified by the following. We're looking only at the short-term effect of the pandemic, maybe 1 or 2 years. And because it is such a short-term process, we can ignore the longer-term processes. That's why we assume population is closed. And this allows some simplification in the mathematics, because we can assume then, because the population size remains constant, we can scale everything and assume population size is equal to 1, and therefore the compartment sizes will correspond to the proportion of the corresponding individuals. Next addition that's specific to COVID-19, so we know that you can be symptomatically infected, so you know that you have the disease, or you could be asymptomatically infected. You can be the carrier of the virus, you can infect others, but you will never know that you're doing this. It's true for many infectious diseases, but it's especially important in the setting of COVID-19. So a certain proportion of individuals become asymptomatically infected, and the rest of them become symptomatically infected. And the last addition to this compartmental model is the inclusion of quarantined and hospitalized compartments. Now, because COVID-19 is such a disease that many individuals encounter serious complications, some of them get hospitalized. Also, some individuals who have these symptoms, but not severe enough symptoms to be put in the hospital, or let's say there is no room in the hospital, as we saw many times, then they're simply asked to quarantine themselves. And notice that the arrows in this case go both ways. So hospitalized individuals, so they may recover, they go to the R compartment or die, same thing for quarantined individuals. But if the pandemic has a very sharp peak, then there might not be enough room in the hospital, and individuals might be released from the hospital once there is no threat to their life, but they haven't actually recovered from the disease. So they go back into the infectious compartment because they may still potentially infect others. Same thing for the quarantined individuals. Individuals may break the quarantine themselves and just not do what they're asked to do. This will become kind of a big feature of this model. And now there are 7 compartments. So this system is described by a system of 7 differential equations. We assume that if you look at the first equation, there are coefficients that modify the infectiousness of asymptomatically infected, quarantined, and hospitalized individuals, because let's say in the setting of a hospital, you have limited contact with other individuals, you're less likely to infect others. Also, we have separate the rates that go into the R compartment. Our removed compartment includes both diseased and recovered individuals, and we have separate recovery rates and COVID-19 induced death rates. These will become important in the game-theoretic model. That's why we separate these two notions, how individuals become part of the removed compartment. So this is a basic epidemiological model. Human behavior does not enter the picture at this stage. And of course, this part is easy. Drawing the diagram and writing equations is easy. The hard part is calibrating the parameter values. So what values do the parameters take? And so Follow knows how to do this, and they fitted the parameters to an actual data in Arizona. And so I think they got a pretty nice fit of this model with the actual data. So now let's look at this pure epidemiological model, and let's see what kind of information we can get from that even before we include the human factor in this model. So this is the effect of quarantine and hospitalization. In the left pane, the solid lines correspond to the baseline parameter values, but dashed line correspond to double quarantine and hospitalization rates. And notice what kind of effect it has. So the peaks appear later in the timeline, and they're lower. This is exactly what we want to achieve, because the total number when infected individuals will anyway remain more or less the same. But if we reduce the height of the actual peaks, then we reduce the burden on the healthcare system, and everyone has a chance to get the proper care, as opposed to very sharp and early peaks. When the healthcare system gets taxed too much, it cannot keep up with the demand. So on the left, the dashed lines correspond to the good scenario, what we want to see. On the right pane, we have the opposite case, when we double quarantine violation and early hospital discharge rates. So the dashed lines now here, they provide much higher peaks, and they occur early in the pandemic. This is exactly the situation we want to avoid. So even before the human factor enters the picture, it's very clear that it's important to provide sufficient hospitalization rates, sufficient quarantine rates, and people who are asked to quarantine, they actually remain in the quarantine compartment. They do not violate the quarantine. But now let's see what happens when we account for that human behavior. So we're going to use a game to model human behavior. So individuals will play some kind of a game. And what kind of ingredients go into setting up the game? Well, we need 3 ingredients. We need to know what are the players in this game, then what strategies they may use, and the possible outcomes. So we need to know the possible outcomes so individuals may make informed decisions. If I do A and you do B, this is what's going to happen. So depending on what you do, I might decide what's best for me to get the best possible outcome. And in fact, only today, because it's November 1st, I have a BOGO sale. So for the price of one talk, I'm going to set up two different games. One game will be played by susceptible individuals, and the second game will be played by symptomatically infected individuals. So infected individuals who know that they are infected. So what strategies will they use? Well, the susceptible individuals, so what drives their behavior? They don't want to get infected. And in the absence of any other measures other than closures and self-isolation, they can either support school and workplace closures as an isolation measure, or they can oppose these measures. With the infected individuals, the situation is totally different. They cannot help themselves. They are already infected. But they may try not to infect others. So it's a completely altruistic behavior. So they may elect to self-isolate or not self-isolate, said, well, I don't care, I'm going to share the wealth, I'm going to infect as many people as I can. So what are the outcomes? How are we going to look at the outcomes? Well, the outcomes in the game, that are called usually payoffs, that given strategy you choose and then given the population strategy, this is what you're going to get. So in case of the susceptible individuals game, the payoffs are going to be based on the disease prevalence, as well as the sensitivities to socioeconomic losses. So of course, if the workplaces are closed, people lose their jobs, they lose their income, and so they incur some very tangible socioeconomic losses because of this. And in case of the infected individuals, their payoffs will be based on the disease mortality and then sensitivity to being socially isolated from other individuals. Of course, I'll go into detail how everything is set up, but this is kind of a general kind of high-level thinking of what goes into constructing such games, how we're thinking during the modeling process. The first game, which is the support for the closure behavior by susceptible individuals, is adopted from another work, another preprint, and the last author of this, Chris Pauch, he's one of the world leaders in this field. So he's one of the early adopters of these methods, and he published maybe up 100 papers or so using game-theoretic models within the epidemiological disease settings. So let's set up the first game with susceptible individuals. So we're going to denote by X sub S the proportion of susceptible individuals that support closure. And because this is a dynamic game, this proportion will change with time. Now, how this affects the epidemiological model? Well, we have this function, which is a time-varying impact of these closure measures. So in effect, it's a step function. So the measures are either turned on or they're turned off. If they're turned off, then there is zero effect. If they're turned on, there is a fixed effect, which denoted by C naught, and I'll explain how that effect then gets implemented in the epidemiological model. So when do we turn on the measures? We turn on these closure measures as long as a certain initial time has passed. We do not turn it on too early, and at least half of the susceptible population supports the measure. If the majorities of the population vote for the measure, we turn it off as soon as less than half of the population supports the measure. So in principle, this may oscillate with time. It may be turned on, off, depending on how the behavior of the population evolves with time. So how do we account how this affects the epidemiological model? Well, we have this beta, which is kind of the basic transmission rate. It gets multiplied by 1 minus C. So if the measures are turned off, there is no effect. If they're turned off, there is a reduction given by C naught. So there is a fixed reduction in transmission rate. Now, how do the behaviors evolve? What individuals use to inform their decisions? Well, again, the driving factor behind this behavior is the desire of the susceptible individuals to protect themselves. And so those individuals who oppose the closure, they're facing the risk of getting infected. Those individuals who support the closure are facing the socioeconomic losses. And here's why this game setting makes sense in this case. If you support the closures, then you face a certain fixed socioeconomic losses, certainly, which depend on time, of course. However, if you oppose these measures, you face the risk of infection, but the risk of getting infected depends on the current state of the pandemic. So let me explain how these payoffs are computed. So E naught is the payoff of those who oppose the closure measures. And how do they estimate? So what's my risk? Well, in this case, we use kind of this bounded rationality principle that individuals don't have a perfect information. They don't know exactly the probability of getting infected, but we can estimate that. So how can we estimate probability of getting infected? It can be estimated by looking at the proportion of currently infected individuals. So based on the reports you see on different websites and from CDC, you can approximately know how many people are infected. They include quarantined, hospitalized, and symptomatically infected individuals. But notice, we don't know the size of the A compartment. We don't know how many people are asymptomatically infected. So therefore, we cannot account for this factor. We don't know this information. All we know is the proportion of known infections. And then we multiply this by the parameter of the model, which is called sensitivity to being infected. So how afraid are we of getting this infection? The payoff for those who support the closures we denote by E1, and it is based on this function which represents accumulating socioeconomic losses with time. And again, there is another sensitivity parameter, that is sensitivity to losses. Of course, populations are always heterogeneous. Different individuals may have different sensitivity to these losses, but in this first kind of simple model, we assume that there is some kind of an average thing, because if population is large enough, then averaging usually provides sufficiently accurate results. So how do individuals decide which the behavior to adopt? Of course, they look which behavior provides a higher payoff. Now, here is a catch. In this kind of game, the payoff is always negative. So there are no winners in this game. What you're looking for is you're looking to minimize your losses. And the easy way to do it is to look at the difference between these two payoffs. Also, in game theory, if you scale payoffs by a constant, it does not affect the outcome of the game. So therefore, because we have two sensitivity parameters here, we just scale everything. So we divide by pi s to get this one single relative sensitivity parameter. So this is sensitivity to socioeconomic losses relative to getting infected. So this is a scaled payoffs, and this is our difference. So let's set up the equation that describes the evolution of this behavior. So the susceptible population then is split into two behaviors. So XS individuals support closure and 1 minus XS individuals oppose closure. And then they interact with each other. They meet with each other and they adopt each other's behaviors based on which behavior is better. So in a sense, if you observe a more successful individual, you try to imitate the behavior of that more successful individual. But then how often you meet this individual depends on these two quantities. So in this equation, which describes the evolution of the proportion of individuals that support closure, first of all, we have the product of XX and 1 minus XX. This is the rate at which they meet each other. It's a mixing rate. Then we have a certain fixed parameter, kappa sub s, which is the social learning rate, so how fast we adopt our behavior. And then in the square brackets, I have this difference in payoffs. So if supporting closure behavior provides higher payoff, this difference is positive. so the number of these individuals will grow. On the other hand, if opposing closure is a better payoff, then this difference is negative, and the number of individuals supporting closure will go down. So the derivative either positive or negative. So this is a standard setup of so-called imitation dynamics. It's one of the ways to model the social learning behavior algorithm. Also, we have this function which describes the socioeconomic losses which accumulate over time. Of course, the longer the closure measures are in place, the more losses individuals encounter. And in this case, so C of t is that step function. So if the measures are turned off, it's equal to 0. So therefore, there are no losses. If it's turned on, it's a constant. So these losses accumulate at a constant rate. We also have this parameter which describes the impact rate of all these measures. But we also, because so it doesn't grow exponentially, we have this decay mechanism that discounts the past losses. So the losses that happened long ago, they are counted much less than the current losses in this function. Now, let's see how to model the behavior of the infected individuals. Now, I'm going to go a bit quicker about this because it's similar in nature to how it was set up in the first game. So we denote by xi the proportion of infected individuals who elect to self-isolate. And how this affects the epidemiological model is that we assume that those individuals that self-isolate, they do not contribute to the spread of the disease. So that's why the I compartment gets multiplied by 1 minus xi. So only those individuals who do not self-isolate, they keep contributing to the spread of the disease. So let's look at the payoffs, how we set up the payoffs in this game. So this model is completely new, so no one has done it before this work. So if individuals elect not to self-isolate, then they face the burden of infecting others. If individuals do elect to self-isolate, then they face the burden of social isolation. But now the payoff for this self-isolation is different and it's fixed. Why is it fixed? Because usually the length of social isolation is exactly the length it takes you to recover. So it does not depend on how the other individuals behave. So therefore, we assume it's just a fixed constant because it's the same for everyone. Whereas the behavior of not isolating, again, depends on the state of the pandemic. So here's what we did, what we decided. We're going to look at how much burden I'm going to cause the society if I choose not to self-isolate and infect others. And what we do is we look at the current death rates induced by the COVID-19. And again, this is a more or less known statistics that can be obtained from public sources. So we use this COVID-19 induced death rate. So the higher the death rates, the more burden we're going to currently impose on a society. And of course, this gets multiplied by how sensitive we are to infecting others. Whereas with the social isolation, we simply have this fixed constant, which we can think of as sensitivity to social isolation. Then we go through the same process. So the evolution of this behavior is described by this differential equation. Again, the two types of individuals, they mix, they meet each other, they adopt each other's behavior. We have this social learning rate in this game for the infected individuals, and we scale the payoffs so that the difference of the two payoffs now includes only one relative sensitivity parameter. So it's sensitivity to social isolation relative to sensitivity to infecting others. So we just make the model dimensionless. You have one single parameter in each case. Now that we set up these two games and we saw how they affect the epidemiological model, let's put everything together. So now we have three more equations. Two equations describes the first game and one more equation describes the second game. And all of these behaviors have now been incorporated into the epidemiological model. So the first two equations include the effect of the closure measures as multiple 1 minus C of t on beta, and the effect of the self-isolation measures is included as 1 minus xi as a multiple on the infected individuals that contribute to the infections. So now let's see what's going to happen when we put these two together. First, I'm going to show the effect of each of the games independently of each other. So I'm going to turn off one of the behaviors, and that is easy to do by assuming that the initial adoption is equal to 0. And if the quantity is 0, it will never grow from 0. So first, we are going to assume there is no infected individuals game. So it's only the susceptible individuals who either support or oppose the closure. And the interesting thing here is that we observe the Goldilocks effect in this case. So let me explain what the graphs show. On the left pane, it shows the proportion of symptomatically infected individuals with time. On the right pane, the graphs show the behavior, so the proportion of individuals who support the closure. The red graphs correspond to low initial support. So initially, only 15% of the population support the closure measures. And notice what happens in this case. We have a very quick and sharp peak of the pandemic, and by the time this peak appears, individuals realize, wait a minute, what have we done? We need to support these closures. So the support grows very quickly, but it's already too late by that time. We have this very sharp peak. The green graphs correspond to very enthusiastic support for the initial measures. 65% of the population support the measure. But here's what happens in this case. Why is bad as well? It's because all this initial enthusiasm quickly wanes down. It goes down on the behavior graph, and that allows the infected cases to sharply rise. And by the time people realize, wait a minute, what we have done, it's too late again, and we have another very sharp high peak. So of course, the right behavior picks up eventually, but it's a bit too late. We still have that. And again, I keep saying that we want to avoid the sharp peaks. That's our goal, avoid sharp peaks. But notice the best outcome occurs in the blue line when the initial support of the measures is a bit middling. So it takes some time for this behavior to be turned on, but it allows to suppress the first peak. Then it goes down. This allows for the second peak to evolve, but because it still it didn't pass enough time, we have this second peak, but the population quickly reacts to that second peak, and they start supporting the closures again. And so in this case, we do not have any sharp peaks. So we spread the cases evenly over time, and this is exactly what we want to achieve. So we have this Goldilocks effect that the middling initial support is it's the best outcome. Neither low or high initial support is going to be good in the long term, which is, it could be somewhat surprising, but that's what the model shows. Next, we're going to turn off the susceptible individual behavior, and we're going to look at the self-isolation behavior. And again, the different colors correspond to different initial support enthusiasm, but in this case, the conclusion is very simple. In this case, it's best to have that high initial support for that measure. So the more individuals are initially willing to support the measures, the lower the peak of the pandemic, and later in the timeline it occurs. So there are no surprises here. But now let's put the two together. So both behaviors are now enabled. So on the right pane, which shows behaviors, the black lines correspond to the susceptible behavior, and the red lines correspond to the infected self-isolation behavior. And here's what we observe. If you look at the solid line on the left pane, we have these two peaks, two waves of the infection. This is exactly what we observed in the United States early in the pandemic. We had these two peaks of the two waves of the pandemic. And in fact, from this graph, because individuals in this game, in this case, they act rationally in their own perceived self-interest. And so therefore, these two peaks of the pandemic, two waves of the pandemic, it could be attributed to kind of inevitable result of rational behavior by humans who try to do what's best for themselves rather than what's best for the society as a whole. However, if you look at the dashed lines, it corresponds to the higher learning rate for the self-isolation behavior. So if individuals switch their self-isolation behavior, if they react in a faster fashion, if they see that the number of cases go up, then more individuals are willing to self-isolate. Then notice this dashed line on the left pane, we do not have that second wave. So if individuals adapt quicker to the environment, then we can avoid this second wave. On the other hand, it's also possible to have multiple waves of infection that persist over time, yet they're fairly small waves. So this is what might happen in the long run. And this is going to occur if the social learning rate for the self-isolation behavior is too high. So on the other hand, we want individuals to adopt to the environment fairly quickly, but if they do it too quickly, like if they're willing to switch their behavior almost instantaneously, it results in this long persisting oscillation. However, this can be overcome if we increase the quarantine and hospitalization rates. So in this case, the dashed line corresponds to 5-fold increase in quarantine and hospitalization rates. And as you can see, it prevents these persisting multiple waves of the infection. So what kind of conclusions can we draw from this? First of all, increasing quarantine and hospitalization rates is very important, and it reduces the disease burden on the society, as well as the burden on the healthcare system, because it reduces the epidemic peaks. Also, if infected individuals are willing to learn this proper behavior of self-isolating, then it will reduce the disease burden, but it can lead to multiple waves of the pandemic if susceptible individuals do not appropriately account for these quick changes in the population. Higher quarantine violation and hospital discharge rates may amplify the infection peaks and lead to persisting waves of the infection over many, many years. And we can battle these multiple waves of infection over a long, long time if we increase the quarantine and hospitalization rates. So there are some, some of these conclusions are obvious, but nevertheless, these conclusions that are supported by mathematical modeling. So we have a reason why it works out the way it should work out. So if there is one thing that you get out of this presentation, it should be this. When something like this, when pandemic hits the world, the only way to get out of it is to work together as a team and to help each other. So let's help each other anytime something like this happens, and we'll all be living in a better world. Thank you for your attention.
Thank you very much. That was a wonderful talk.
And before we move on to Q&A, I think I deserve a couple of plugs now. If I can have 1 minute for some ends.
Absolutely.
So first of all, as I mentioned, this work led to kind of building a team, and we got $1 million NSF grant that starts in January of next year. In particular, this grant will fund some graduate students. So it will cover tuition waivers, it will give the stipend. So in particular, I'm hiring, so I'm looking for 1 master's students to start next fall. So if anyone is potentially interested to work in this kind of cutting edge models, get paid stipend from NSF grant, which means there is no teaching obligations. It's not an assistantship paid by the department. So your main focus will be to do research in this direction. Then please get in touch with me. Ask me any questions. I will be happy to provide more details if you're potentially interested in this topic. And if you're interested in coming to UNC Greensboro and be a master student for 2 years here under this program. And another small plug, less important, is that if you like this presentation, you might want to check out my YouTube channel. It's called Mathematics Flipped.
I'm sorry, can you say that again? Mathematics what?
Mathematics flipped, like a flipped classroom approach. Yes.
I see.
These
Thank
are all
you.
the plugs.
Yes, thank you so much. We really appreciate this talk, and our students, when they all watch it, we will make sure to mention these two items. I'll stop the recording.
But mostly I'm interested in finding a good student who would be interested in working on this. And that is going to be paid by NSF grants. So we have money for conference travel, for supplies, equipment, everything.
I have a question.